So, an overview of the solids that we're going to look into are as follows. They're actually grouped into two main groups. We have your polyhedrons, and then we have your curved surfaces. So polyhedrons, later on we're going to define them, and then the curved surfaces. So the polyhedrons will give the formal definition in a while, but basically the faces are polygons, while in curved surfaces, the faces, or the face, so to speak, is a curve, not a polygon. And these would have somehow some would have counterparts with each other. Because for polyhedrons, we're going to talk about prisms, then pyramids. Oops, I don't think that's a good moment. There's only two. So that would be the prisms and then the pyramids. And then for the curved surfaces, their counterparts would be, for prisms, we have your cylinders, and for pyramids, we have your cones. A special curved surface solid, which is a sphere, is something that we'll also talk about at the end. So let's talk about these one by one. So first, oops, not here. I think we just move this. There you go. So first, we define a polyhedron. So a polyhedron is a solid in which it's bounded by polygons at the edges. Now, polyhedrons are divided into three. Oops, we forgot the third one here. Somehow you can see it's a counterpart of the sphere, which are here we have our platonic solids. There you go. So that completes our chart. So the bounding faces of the bounding polygons, which are the boundaries of our polyhedron, are what we call the faces. And the intersection of each face are what we call edges. The intersection of the edges are what we call the vertices. So the surfaces on the side are what we call lateral faces, and their intersection is what we call the lateral edge. Now, polyhedrons, like what we mentioned, are divided into prisms, pyramids, and platonic solids. Platonic solids are those polyhedrons whose faces are regular polygons. That's why somehow it is a counterpart of the sphere. Because the sphere can be thought as the solid counterpart of a circle, which is a circle is defined to be equidistant from the center. So somehow it's close to the idea of being regular. So for platonic solids, we have the following. We have 4 regular triangles combined together. We have a tetrahedron. If we have 6 squares, we have a hexahedron. If we have 8 regular triangles, we form an octahedron. If we have 12 pentagons, regular pentagons, we form a dodecahedron. And we have 20 regular triangles, we form an icosahedron. And these are the platonic solids. Although we're going to focus much more on prisms and pyramids, it's also good to take note of the platonic solids, which again, their faces are made up of regular polygons. When we say regular polygons, it means that the measures rather of their sides and angles, the measure of the sides are all congruent, and the measure of the angles are all congruent as well. Now, the first type of polyhedron that we're going to look into is a prism. So a prism is a type of polyhedron whose congruent bases lie in parallel planes. So the bases of a polyhedron are congruent, these, and they lie on parallel planes. So the planes must be parallel to each other so that we're going to have a prism. So we can also describe a prism as a 3-dimensional solid formed by dragging the polygon through space to a certain height without rotating or tilting the polygon. So imagine this triangle being stretched out from here to there. That's one way also to describe a prism. And we have different types of prisms as we have different types of polygons. Triangular prism, rectangular, square, pentagonal, and so on. Now, a prism whose bases and lateral faces are parallelograms, such as this rectangular prism and this square prism, they are collectively known as parallelepipeds, or singular, parallelepiped. If a rectangular parallelepiped like this that's more commonly known as your rectangular solid or rectangular prism, since it's one of the most common solids that we can see. Now, a cube is a special type of prism whose faces and edges are all congruent. Now, some terms related to solids, to prisms rather, the lateral surface area or the lateral area of a prism is the sum of the areas of its lateral faces. For example, here we have 1. We have this lateral face 1, 2, 3, and the one in front, that's 4. We have 4 lateral faces. So if you want to find the lateral area, you find the sum of those 4 areas. The total surface area includes now the area of the 2 bases that we have. And take note, usually when we think of base, it's the one on top and the one down below. But that's not always the case. It may depend on the orientation. In this case, the base is the one on the left and right side. But the total area of that would be the total surface area, which is the lateral area plus the area of the 2 bases. Further, we also define the volume of a prism as the amount of space it occupies. So the amount of space inside this prism is defined to be the volume, computed in prisms as the area of the base multiplied to the height. This is where the idea of a prism being a stretched polygon through space comes from. Some additional formulas: the diagonal length of a rectangular solid, the line segment that may connect 2 opposite vertices not on the same face, because that would be a diagonal of the specific face only. That formula is given by the square root of L squared, which is length, W squared width, and H squared, H for height. The diagonal length of a cube, though, is S times the square root of 3. With that, let's take a look at some of sample problems regarding prisms. For the first one, we have our problem here. We are asked to find the volume of a right triangular prism in which the height is 100 centimeters and which the base is a right triangle with a hypotenuse 30 centimeters long and an angle of 60 degrees. So, since we are told that this is a right triangular prism, it is a prism whose bases are right angles. So if we have that for number 1, we can draw probably a right triangle like this. Here. And we draw another one. We can do a rough sketch of our right triangular prism. There you go. Alright. And then we are told that the height is 100 centimeters. Remember, when we say we're talking about the height of the prism, it should be the distance between the bases, which would be from this base to this base, because these two are our right triangles. So therefore, let's put the right triangle amongst. Therefore, that distance, which can also be here, that's your 100 centimeters. And then the hypotenuse of the right triangle is 30 centimeters long. Here you go. 30 centimeters long. And it has an angle of 60 degrees, which doesn't say where it could be. So it can be here, or it can be here up above. Let's just choose this one here, 60 degrees. So to find the volume of a prism, we are, again, the volume of a prism is given by the area of its base times height. And we already have the height, which is 100. Just now need to figure the area of our base. Since it's a right triangle, we can always start off first that the area of a triangle will be 1/2 the length of the base of the triangle times the height of the triangle. And usually in a right triangle, that would just be the sides, or the legs rather, of a right triangle. So from here, we can assign this as our base of the right triangle, and this is the height. Maybe we'll change h to h sub, there you go, h sub triangle, so that we're talking about the height of the triangle. And as you can see, it's a right triangle with an angle of 60 degrees. So we can use trigonometric functions to solve for the length of the base and the height of the triangle, since we have an angle and the hypotenuse. So to solve first for the height of the triangle, we can say that, let's change that. We can say that rather that the relationship between the height of the triangle, 60 degrees and 30, is given by sine. Sine 60 degrees is equal to the height of the triangle over 30 centimeters, the hypotenuse. Similarly, we can also have the relationship between 60 degrees, the base, the length of the base of the right triangle, and the hypotenuse. In this case, we have cosine 60 degrees is equal to the length of the base times 30 centimeters. Cross multiplying, we're going to get the height of the triangle will be 30 sine 60 degrees, and that is equal to 15 square root of 3 centimeters. On the other hand, for the base of our right triangle, that's 30 cosine 60 degrees, and that will be equal to 50 centimeters. Now to find the area of our triangular base, that would now be equal to 1/2 times 15 square root of 3, which is our height, times 15, which is our base. Therefore, we're going to have the area of our right triangle would be 225 square root of 3 over 2 squared centimeters. This area now is the area that we use for this formula. Therefore, the volume of the prism would be the area of our right triangular base, which is 225 square root of 3 over 2 square centimeters. Let's not put the unit yet. Times the height of the prism, which is 100. This now gives us a volume of 11,250 square root of 3 cubic centimeters. Therefore, the volume of our right triangular prism is 11,250 square root of 3 cubic centimeters. Now let's look at number 2. The base of a triangular right prism are 12 centimeters apart. Find the volume and the total surface area of the prism if one side of the equilateral triangular base measures 6 centimeters. Note that the area of a triangle can also be computed by one of our formulas that we used before. The area of a triangle is equal to 1/2 AB sine. Now, one thing that we did not took account in the first problem, because most of the time it's understood, is the concept of right and oblique prisms. When we say a prism is right, that means the bases, the height, not the height, but the edges of our prism is perpendicular to the bases. For example, if I have this triangular base, I have this, I have that, and I have this, then I connect these. So more or less, this is a triangular right prism because the edges that connect the bases are perpendicular to the bases. However, if it's oblique, it will look something like this. If we have our same triangular base here, it can look, it may not be perpendicular, it will look something like this. There you go. Here. So the prism might look something like this. and that is oblique because these edges here are not perpendicular to our bases. Most of the time though, problems that are given to us say would have that quote unquote default setting that most of these prisms are right. I just pointed it out here to let us know that there's also an oblique prism. So in this case, we're going to use a right prism, a triangular right prism. So these bases are 12 centimeters apart. Although I made it a bit big, but let's assume it's 12 centimeters. Now, we are asked to find the volume and the total surface area if one side of the equilateral triangle, so the base is an equilateral triangle and it measures 6 centimeters here. And if this is 6 centimeters, it's automatic that these two are also 6 centimeters. 6 centimeters. Now, so let's first find volume because the problem says find the volume and then total surface area. So let's look for the volume first. So the volume of a prism is once again the area of the base times the height. So this is where this comes in because we are asked to find the area of an equilateral triangle. Now, do take note that if we have an equilateral triangle, here and here, if we have an equilateral triangle, it's more or less, it's also an equiangular triangle, meaning these angles are congruent, and that's a total of 180 divided by 3. This will be 60 degrees. And if this is 6 centimeters, 6 centimeters, and 6 centimeters, using this formula, we can find the area of our triangle, or the area of our base. The area of our base will then equal to 1/2 times 6 times 6 times sine 60. Therefore, this will become, this is 36 times 1/2, or you can think of it as 3 times 6, that will be 18 times sine 60. Then that will then be equal to 18 times square root of 3 over 2, which will end up as 9 square root of 3 square centimeters. Now that we know the length of, the area rather, of our base, and we know the height, therefore the volume of our triangular right prism would be the area of the base, which is 9 square root of 3 cubed square centimeters times the height of 12 centimeters. That will then give us 108 square root of 3 cubic centimeters. That's our volume. We're going to write also at the end. Now for the total surface area, that is the area of each lateral face, the lateral surface area, the lateral area, plus the area of the two bases. And we already know the area of the two bases. That's 9 square root of 3. We just have to multiply that to 2. Now for the lateral area, we have 1, 2, 3 lateral faces, which are rectangles whose length is 6, width rather is 6, and the height, the width of 6 and the length of 12. So therefore, the lateral area will then be the width of 6 times 12 times 4. Not 4, sorry, 3. Because there are 3 bases. So there you go. So this plus twice the area of the base, that's 9 square root of 3. So solving this, we're going to get that 6 times 12 times 3. This will give us 216 plus 2 times 9 square root of 3. This gives us 80 square root of 3 square centimeters. Therefore, we say that the volume is equal to 108 square root of 3 cubic centimeters, and the total surface area is 216 plus 18 square root of 3 square centimeters. Now, the counterpart of a prism on curved surfaces is a cylinder. First, we define a cylindrical surface to be the surface generated by a straight line which moves along a fixed curve and which remains parallel to a fixed line not on the curve. So let's try to illustrate that. For example, we have this straight line here. This straight line. And it's also parallel to this line. However, it moves along this fixed curve instead. So of course, once you move along there, the tendency is you're going to have this, you have this here, and then you all move, move, I hope I can copy what there. Oops, isn't it the same? So there you go. Somehow it's the same. Yeah. So this is what we call now a cylindrical surface. Now, a cylinder will then be a solid bounded by a closed cylindrical surface. So this is open, we close that, we form a cylinder. And the cylindrical surface becomes the lateral face, and the two parallel planes are the bases cutting all the elements of the surface. So for example, if we would have this curved surface here, and then we would have the same curved surface, for example, we would have this curved surface, and then we would also have this curved surface. Assuming they're the same, actually, that can also be considered as a cylinder. The most common cylinders that we see are those cylinders with circular bases, and we call them circular cylinders. And the most common of those circular cylinders is what we know, is what we're more familiar with, the right circular cylinder. That cylinder is a right circular cylinder if a line segment drawn from the center of one base is perpendicular to each of the bases. For example, if I draw this line segment from the center down below, and that turns out to be perpendicular here and there, then it's a right circular cylinder. Otherwise, it's oblique, just like what we showed a while ago. It can look something like this. Say, for example, we have this circle here, then it will have something like that. So that's what we call an oblique circular cylinder. The surface area of a cylinder is composed of two circular bases and the lateral face of the cylinder. So for the surface area, it's this one here. We are covering the area of the two circles plus the cylindrical surface, which happens, if you go to stretch it out, which happens to be a parallelogram, which looks like a rectangle. So we can get this surface area by getting the area of these two circles plus the area of this, which is the length of that is 2 pi r. That's the length of this circle here. That's the width of the base of this parallelogram. And then the height, this length here, is the height of the cylinder. That's why the surface area is shown by this formula. Now, for the area, since the cylinder can be thought of as a prism with two circular bases, the general formula for the volume of a prism may be applied. Now, oops. There you go. So, the formula for the formula for volume of a prism rather is space times height. The area of the base is a circle, so that would be pi r squared h. Pi r squared rather. First, that is the area of the circle. The h is the height that we drag with. So therefore, oops, there you go. This h here, this b is the pi r squared, while the h that I just removed, I'll add it again, is the height of the cylinder. Therefore, the volume of a circular cylinder, whether it's right or oblique, is pi r squared h. while the total surface area of a right circular cylinder is given by the area of the two bases, that's 2 pi r squared plus pi r h. 2 pi r h. That is 2 pi. Now, let's solve some problems regarding cylinders. For the first one, the lateral area of a right circular cylindrical tank is 48 pi square meters and its volume is 72 cubic meters. We are now asked to find the altitude of our tank. So, we know that we have the lateral area of the right circular cylinder. So if we have a circular cylinder, we draw it like that. So the lateral area, only the one around, the lateral area is 48 pi square meters. While the volume of the same cylindrical tank is 72 pi cubic meters. Now, for the lateral area, we can actually solve an expression for the height here. Because the lateral area is just the area around it, and we mentioned a while ago that it's that parallelogram whose length is the circumference rather of the base, and then the width is the height. So the lateral area would equal to 2 pi r, the circumference of our circular base, plus the height, times the height rather. That's why it's 2 pi r h. Now, since the lateral area is 48 pi, that will be, this is equal to the formula 2 pi r h. So if we divide both sides of the equation by 2 pi, pi gets cancelled. Therefore, I'm going to get the expression that 24 is equal to RH. Therefore, if we divide both sides by r, h will be equal to 24 divided by the radius of the base. Now, we can use this expression to find the height, in our, not the height. Since we're looking for that, we need the expression for r. So let me redo this part. I apologize. So this is, the 24 is again equal to RH. We need to solve for h. So we need somehow an expression that we can insert in the volume to solve it later. It will be more clear in a while. So I need expression that leaves with h. So therefore, I need to divide both sides by h. The expression is left with r. So r is equal to 24 over h. Now, why do we need an expression for r? What is that for? In the volume of the cylinder is pi r squared h. And we know that the volume is 72 pi, that's equal to pi r squared h. If we would like to solve for h, then we can substitute the value of r here. And then we will going to have an equation with h alone. Now, would it work if we started with volume first? It would, but r is squared. So that makes it a bit more complicated. That's why we started with the lateral area, because r is just first degree. Now, substituting the value of r here, I'm going to get 72 pi is equal to pi times 24 over h squared times h. Now I'm going to get 72 pi is equal to 24 squared is 576. That's pi times 576 times h squared times h. So now we have to solve this in terms of h. 72 pi will then be equal to that's 576 pi over h, because that gets cancelled. Cross multiplying, I'm going to get 72 pi is equal 72 pi times h is equal to 576 pi. Divide both sides by 72 pi. h will then be equal to 8 meters. And that's what we're looking for, the altitude, the height. Therefore, h is equal to 8 meters. Again, just to clarify the process that we have done here, we wanted to find the altitude given this. And we know that the altitude or the height is part of both formulas. So we want to find a way to solve for h. Now, if we do this here, we can divide the lateral area by 2 pi r. But we need to find the value of r. And most probably, we can get it here. It's just that this is r squared. So that process might be a bit more complicated. That's why we started with the lateral area instead. We get an expression for r that we can substitute to the formula for b. So that the equation that we're going to get is just a single variable h. Now, for the second problem, you are wrapping a stack of 20 CDs. Each CD is a right circular disc with a height of 1.2 millimeters, and a radius of 60 millimeters. What is the minimum amount of wrap needed to cover the stack of 20 discs? So, that means if we're going to stack 20 discs, we're going to form a cylinder. It can look like that. The radius is the same because they're just stacking, it will not change. And this will now be at 20 CDs stacked, 20, 1.2 millimeters stacked. And that's 20 times 1.2 because 20 meters stacked, so that's 21.2s. And that will give us a value of 24 millimeters. And if we need to wrap this cover around, therefore we need to find the total surface area because it's a cover. So the total surface area of this stack would be equal to twice the area of the two bases plus the area of our lateral face. So therefore, this becomes 2 pi times 60 squared, that's the radius, plus 2 pi times 60 times 24. Therefore, I'm going to get 60 squared, that is 3,600 times 2, that will become 7,200 pi, plus 60 times 24 times 2, becomes 2,885. Therefore, adding that, the total surface area, which is the minimum amount of wrap we would need, would be 10,085 square millimeters. So those are some sample problems regarding cylinders. And a long while ago, prisms.